right, the recording is on. So ho, everybody. So this is the last session of our regular webinar on vector symbolic architectures and hyperdimensional computing. So I'm very happy to see so many of you joining. So thank you very much for being with us. And today we have Denis Kleyko to present his and our recent surveys on vector symbolic architectures. So without any further delay, so I leave the floor to him, and then I will make a short announcement by the end of his talk. Denis, please.
Thanks, Evgeny. I hope you can hear me well, and probably, hopefully, the slides are visible as well. Can you confirm it, Evgeny?
Yes. So everything is all right.
That's great. So yeah, okay. Let's start then. So as Evgeny mentioned, I'm today going to overview our recent work on which was making a survey of hyperdimensional computing, aka vector symbolic architectures, and this is a joint work with Dmitry Rachkovsky, Evgeny Osipov, and Abbas Rahimi. And I saw already Abbas and Evgeny in the audience, and Dmitry is probably not going to join due to the time difference. Oops. Yeah. Okay. Yeah. So now we can navigate. So as you can see on the slides, due to some logistic reasons, so the survey has been chopped into two parts, and I'm going to walk you through both of them today. And of course, probably it's best to start with the motivation for my talk today. And the motivation is I see it like a double-edged sword. So on the one hand, of course, I want to pitch for the survey and sort of give a gentle introduction into some reasoning behind we had when we were doing it, and also maybe definitely go through the structure of the work, and sometimes just zooming in into particular aspects, and just there is no specific reasoning why these aspects were chosen. So it was mainly my personal excitement about certain aspects of the area. And also the second, of course, motivation is to open the floor for discussion, and probably maybe even perhaps offline discussion later on with some of you in order to get a feedback, because there is always a room for improvement, and we are happy to get the feedback and maybe see some of the aspects which we might have not included, but by some chance, or maybe there are some certain aspects of the work which can be improved. So basically getting the feedback is another motivation for this talk. Of course, it's exciting to give the kind of to sort of wrap up the year and VSA webinars with this kind of a general talk. So when it comes to our personal motivation, why would it make sense to make such a survey? I could immediately think about just trying to make it laser. Yeah, about three motivation points. Why right now, and why in principle it's a good idea to have a kind of survey of the area, and why now? And of course, the first thing is that it's highly interdisciplinary, and we all have different backgrounds, and we know, which is quite exciting, that there are works touching different aspects, like going from artificial intelligence, touching cognitive science, neuroscience, some theoretical work. It's almost like a pure math. So it's exciting the area is highly interdisciplinary, but at the same time it makes a bit of a challenge, because works are published in different places, and it might be a little bit hard to keep track of what's going on and where different works has been published and so on. So therefore, it would be nice to have some kind of handbook which would just allow you to see sort of general view of the area and, you know, immediately give you some sort of pointers and directions and initial feeling like what has been done within a particular direction of the area. And of course, what's the most exciting is that at least looking at the number of publications which been published over the years in the area, we can think about it as a good proxy into the size of our community, and we can see that in the recent years it's been a pretty decent increase in the publication activity, and of course it's, we all know that there are new people joining the area, and we also think that would be exciting to have a single place which would provide like a gentle tour into the area. And when it comes to the structure of the work, there is, of course, first we focus on the fundamentals, on like general motivations for VSAs, why they exist, and what were historical reasons for their appearance. And then talking about the basic components of any VSA model, and an overview of the existing models. So yeah, I just call it a zoo of models. And of course, an important aspect of fundamentals is various approaches to data transformation. How do we take our data from its original representation, and how do we lift it into a high dimensional space for further manipulations? And these aspects, they are covered in the first part of the tutorial. And then, of course, so once we cover the fundamentals, we can think about applications. So what are the applications of VSAs? And I will talk more about it in the second part of my talk, but like on a high level, we've identified like 3 types of different applications. And as a separate part, which also can be seen, of course, as an application, but due to its like unique setup, we thought that it's worth talking about like cognitive aspects separately. And it's like, and cognitive, it's cognitive computing, cognitive modeling, and cognitive architectures. And these parts are covered in the second part of the survey. And one thing which we haven't touched in the survey, and that was done deliberately, was the hardware aspect, the aspects of implementing VSAs in hardware. And that was done on purpose, just because at some point into the work, we've realized that it's like a large topic of its own, and it was just, the project was just getting too large. So we decided that aspect should be left, probably, for separate work. And so, of course, prior or in the process of doing the work, a natural question appeared that was, do we already have a single source of information where we would get all the aspects, all the important aspects of the area, like where the work which would cover all the aspects of the area. And we've identified several prior papers which are here, and we were trying to do some qualitative analysis to see like how different aspects of the area are being described in these works. And of course, we realized that there are several aspects, such as like representation of symbols and sets with hypervectors that are like covered almost in every single paper. So it's almost like it's a compulsory introductory section almost in any work on VSAs and energy computing. But then there are certain aspects which haven't been covered to the best of our knowledge, and such an example would be like an overview of the different approaches to form hypervectors from 2D images. And roughly, for the first part, these aspects can be, again, classified in what I've mentioned into motivation, basic components and models, and transformation into hypervectors. And I will now just walk through some, through essentially certain aspects of each of these three large items. Of course, we start with motivation. And the story we have in the survey, I think that's like a common sense in the area. I don't think that we found any drastically different story of the area. And it's mainly about a debate which was happening largely in the 80s between connectionist community, which is about artificial neural networks, and the symbolic AI, or which is sometimes called good old-fashioned AI community. Talking about disadvantages of both communities. And there are several a few important works, and one of them is Superposition Catastrophe, which essentially suggests that you need to have certain mechanism in order to be able to represent compositional structures in distributed representations. And here, an example here that probably very well-known example, when we have a geometrical shape and its property, let's say a red square, and we're trying to represent several of them, like a red square and a blue circle. If we don't have, and now we know, if we don't have the binding operation, if we only use the superposition operation, the bundling, that would be an issue, because we would get a superposition catastrophe, because there is no way to know which property is identified with which geometric shape. So that was one of the issues. Of course, another famous piece of critique of the connectionism is a work by Fodor and Pelushin, which is about composition, decomposition, and manipulation of structures. And later on, a decade later, essentially, there were challenges posed by Jackendorf. That was about modeling the language. And of course, I shouldn't probably talk too much about it. So we have Ross in the audience, so he probably can say more words about this. But this is what we found as a motivation, and I don't think that it's in any sense radical. I think that this is a common sense which we all have in the area. And of course, the basic component, this slide is absolutely redundant for this talk. I just added it for the completeness. So that, of course, we know that for any VSA model, so there are certain basic ingredients, and they include representation, dimensionality of representation should be high, a source of randomness, a way to measure similarity between representations, a way to store your basic vectors, which we often call item memory or cleanup memory, and a way to manipulate your representations, which is operations and representations. And there are three of them: the binding, superposition, and permutation. And probably the view to which we converge in the survey was that essentially permutation and binding operations, they're doing the same purpose, so they both essentially binding operations. So this is just we kind of advocate the view that these are two types of binding operations. So binding by some multiplicative operation, and binding by permutation, essentially. And of course, the beauty of this is that, since these are components are basic, there's no precise way to define this basic component. And of course, this gives a large room for defining different VSA models. And I think it's pretty exciting that already almost 25 years ago, Tony Plate was already trying to make a summary of the models existing by then, and so it was a combination of essentially models working with distributed representations, and his comparison table in that work included by that time the existing frameworks, such as holographic reduced representations and binary sputter codes and frequency domain holographic reduced representations. So I will call them Fourier HRR. And then later on, I think that was more of a recent movement. We also had a paper in 2017 where we focus on summarizing known VSA models. And of course, it's important to mention the very recent work by Kenny, Per, and Peter, where they go into detailed comparison and like in details consider properties of binding and unbinding operations. And in the survey, we've decided to provide maybe a bit less details because that was not the only focus of the survey, but we've made a similar table with which would specify the existing frameworks with existing models for VSAs, and probably the red rectangles which I have here. These are, I think, points which are worth discussing and which are worth mentioning. So first, of course, tensor product representations. And tensor product representations, we know that there is a tricky aspects, right? Whether to consider them to be a vector symbolic architecture or not. It essentially depends on whether we say that fixed dimensionality of representation, whether it's like compulsory property of a VSA model or whether it's not. And we felt that since like tensor product representations, they were essentially the source of inspirations for many of the like further models of VSA. So that's at least important to mention them, and we provided that note about, of course, the growing dimensionality. Another framework which is modular composite representation here, MCR. We've realized that this model was in a way overlooked by many of the others, but I think most of the papers which would provide the summaries of VSA models. And it was also interesting to actually see that there is a pretty strong connection between modular composite representation and sparse block codes. That they're extremely similar to each other, but of course, when these two works were done, they were done like essentially independently without drawing this connection. And probably the final point on this slide is that geometric analogy to holographic reduced representation. It's like, it feels like it's an interesting model, but at the same time, it didn't get much of an attention from the area, and probably makes sense because like neither Clifford algebra nor geometric algebra is like a common knowledge. So it's a like highly specific area of math. But we've included this framework and indicated that it might be worth taking a deeper look to see whether there is something to benefit from the geometric algebra, because in principle we have this opinion in the area that any framework is in principle quite the same. So they're all comparable in what you can achieve with one model, you can get with the other ones. But at the same time, and I will mention this later when talking about locality preserving encodings, it looks like at least Fourier holographic reduced representations, they have quite a nice property for naturally like representing these locality preserving encodings, which is a little challenging to get, let's say, when it comes to binary representations. And so that brings a question: is there something interesting if we even, if we go even further and like into a more abstract space? Is there something? Would there be some unique feature which we might get there? And of course, like we provide no answer to this question, but it's worth thinking about it. And here I think it's an interesting thing which we haven't really covered deeply in the survey, but there is an interesting aspect to think about, like why do we actually have like that many models, that many VSA models? And I think that there are like several reasons for that, and that's my personal opinion. And I think that's about evolutionary development and about different initial assumptions when constructing the models, and partially probably different mathematical backgrounds of people who've originated and who came up with the ideas for the models. But we of course can see some of these trends, like, let's say, like when going from tensor product representations to holographic reduced representations, that was about kind of an advancement going from getting the fixed dimensionality of representation. So we're just fixing it to n. So dimensionality is not growing anymore. And when like going from holographic reduced representations to Fourier holographic reduced representation, that's about simplifying the binding operation. So going from Rayleigh involving circular convolution into a very simple Hadamard product. And then like we can go from like, we can see at least like how going from Fourier HRR to binary sputter codes, we can get from real value data into binary representations, and going from like binary sputter codes to multiplied permute. We can see a simple binding operation now in the real value domain. And also it's important to know that multiplied permute was probably the first model to really popularize permutation operation. And also nowadays I think there is also like another view for why it's worth having all these models, and we think that's about sort of we sort of advocated this view in a recent paper like earlier this year, where one can make a nice connection with different VSA models and Mars levels of information processing device, like in Mars information processing hierarchy, where we have several levels, going from like low level where we implement things like where the hardware lives, and the algorithmic level where we think that like VSA should be positioned, and then the application level where certain functionality is achieved via the primitives at the algorithmic level. And an interesting property here that it seems like that different VSA models can fit better to different types of hardware implementations. And it's nice because now it allows you to like, based on whatever like hardware you're thinking about, you can try to find the best VSA model for it. But then the other high-level primitives, they're almost the same in all VSA models. Of course, there are like peculiarities, there are certain differences, but in my opinion, sort of the similarities, they outweigh the differences. And just to give us some example, again, so that's not a part of survey, but I think it's nice to think about it, that we have an examples where, let's say, binary or bipolar models, there are lots of papers talking on how to use them on using FPGA, using digital hardware, and also another direction is using like emerging devices such as membristive devices. When it comes to holographic reduced representations or real valued representations, there is like group of Chris Elias, they do lots of work of like using such representation and rate-based coding in order to map it to spiking neuromorphic hardware. And here at the Redwood Center, there is another idea on how to work with spiking neuromorphic hardware, but instead of using rate encoding, using the phase-to-time mapping. And then in this case, Fourier HRR becomes a very, very useful and very convenient abstraction level to think about such an encoding. And that's quite nice. So this is quite different types of hardware. But for each of them, there is a nice connection to one of the VSA models. And then one can just abstractly continue thinking in terms of VSA operations. Like assuming that someone fixed the the hardware aspect and provided you with an implementation of VSA primitives in that hardware. And I feel that there is now a movement in that direction. So wrapping up with the models, let's switch to data transformation into hypervectors, and that's of course an important aspect, because even like getting back to this picture, of course, like it's nice to have like the most basic operations on VSAs, but at this algorithmic level, it's not only about the most basic operations. It's also nice to have like a sort of high-level primitives where we know how to like use a chain of the most basic operations to achieve something, and that's what I mean by data transformation. And of course, there is a lot like certain aspects of representations is about symbolic structures, is about representing symbols and set sequences, graphs, so basic data structures, and I'm not going to touch much on them, but I'll just probably use this slide as an opportunity to again advertise this publication, where we provide a sort of tutorial-like introduction into representation of data structures, which we internally call a cookbook. And then the two other things related to data transformations, which I would like to talk about, are 2D images and numeric scalars and vectors, because these are more of a representations which require some similarity preserving properties. Starting with numeric scalars and vectors, we've identified three different types of, well, three ways of representing scalars into hypervectors. And one approach, we call it compositional approach, and I will spend a few next slides going into the details of a compositional approach. But the high-level idea with a compositional approach is that we can create representation, meaning hypervectors, for individual components of our numeric vectors. So like we can represent scalars. And then we can use either binding or bounding operation in order to create representation of a numeric vector. So in that sense, it's compositional. We first only create representation of scalars, and then we compose it using VSA operations. The second approach, which I'm only going to describe here, is a random projection-based approach. So in this approach, we would use a random matrix, and we would use it to project our numeric vector into the desired n-dimensional space, likely using some component-wise activation function. And the examples of these activation functions might be, it can be cosine, it can be TNH, it can be sine function, it can be k-linear stake-all, and so on. And this approach is tightly connected to random Fourier features, which is a well-known technique in machine learning. And it turns out that random Fourier features in turn are connected to a compositional approach. So these approaches are not fully isolated, but I still think that it's nice to think about them separately. And the third approach is about explicit receptive fields. So this is a case where a certain dimension of our distributed representation is associated with some activation area of the space, and we're going to activate the area of the space if certain components of our original numeric vector, if they're going to activate this receptive field. And there are several encoding techniques for getting sparse representations, but there are also ways to get real valued representations using a well-known radial basis functions. And so let's go a little bit into the details of the compositional approach. I think what's nice about the compositional approach is that it's very intuitive, and there are very basic techniques, which are probably not surprisingly, but which are, to my feeling, they are dominated in the current papers which are related to VSAs and need to use locality preserving encodings. And probably the most simple technique are the thermometer codes. And the thermometer codes are sort of secretly behind most of the papers these days, I feel, which use similarity preserving encoding. And that's simple in the sense that we can begin with an empty vector, and in order to represent the next level, we just continue activating a number of components of a vector until we activate all of them. And so, like, of course, a natural question would be that it looks weird because here the density is changing, and that's not usually the case in the way we represent things with VSAs. But we can do a simple trick here. When we talk about binary or bipolar vectors, we can just take one random vector and take all these codes and do either Hadamard product or XOR operation with that random code. And so immediately we would get fully dense vectors, but their internal, the internal relation to each other would be preserved. And so that's what I mean by like this coding structure is used like kind of secretly, but by most of the papers, because these papers like introduce this encoding scheme through the point of like starting with a dense random vector and then changing certain components of this dense vector. And it's probably worth mentioning that so a nice tool to think about like what's going on with a particular encoding scheme is to look at the similarity kernel. And what I mean by similarity kernel is like when we pick a vector representing certain level of our encoding, and when we plot the similarity between this vector and all the other levels in our code book. And so what we see for the thermometer codes is that essentially thermometer codes allows us to use translation invariant kernel, which is of a triangular shape. So essentially, this encoding literally gives us a triangular translation invariant kernel. And there are other encoding techniques, and so one of them is also is a float coding, which is related to thermometer codes, but we have different. Here we have fixed density of vectors, which again might be a nice property if we want to work with sparse representations. And then there is also a technique which is called a scatter code, and a feature of the scatter code is that they provide us with a different type of the similarity kernel. This is more of like sort of an exponentiated triangular kernel. And so I think what's nice, and I think it's relatively recent thing in the community, is that we've now like started to converge, and you know we started to make a connection between the similarity encoding techniques and kernel methods in general. And so a nice thing about, for example, Fourier HRR approach is that we can actually be pretty flexible in the way which similarity kernel we use, and there were already a couple of webinars given on that encoding technique. One by Kommer earlier this year, and one by Fritz. That was probably done a month or 2 months ago. So what I just want to say here is that so when it comes to representing scalar values with G computing, so probably the most generic framework to think about such representations is to think in terms of what is a kernel, similarity kernel, which is defined by your encoding technique. And some of the encoding techniques can be extremely flexible, and here I just show you a few ways of a few examples to see how the phase distribution from which we draw our random vectors in FHRR model would affect the similarity kernel which emerges between different representations obtained with such an encoding. And some encoding techniques, they're pretty rigid, like thermometer codes. Yeah, they only allow you to work with a trend kernel. And so that was it about locality preserving encodings. And a little bit related topic is representation of 2D images. And for 2D images, we also identified 3 different approaches to encode 2D images into high-dimensional vectors. And one of them is a permutation-based representation. And the idea here is that we think either in terms of like pixel values themselves, or in terms of maybe features extracted from the image, which are connected to certain location on the image. And so in this case, we can use 2 unique permutations, one being defined for x-axis and the other being defined for y-axis. And then by multiplicatively applying these permutations for a given position, we can encode a particular location on the image. And when it comes to these permutations, there are 2 approaches. Probably the most common one is to just use random permutations, but then there is an issue with this approach, issue in the sense that even like pixels that are next to each other, their representations are going to be dissimilar. And then there is an approach to do similarity preserving permutations. And in this approach, so the idea is similar to locality preserving encodings in the sense that the pixels that are located nearby, their representations, they're going to be similar to each other. And in absolutely the same spirit, we have also like key value or role filter binding based representation. This is when we assign hypervectors 2 positions on the image. And one way again to do this, assign completely random vectors. And in this case, we are into the same issues with random permutations, nearby images that is similar. And another approach would be to use now similarity preserving encodings. And in this case, now we can just use one of the encodings mentioned a couple of slides ago in order to define a similar, like such representations of images that they're going to be similar, like vectors of nearby pixels, nearby positions, they're going to be similar to each other. And of course, the issue with both approaches is that if we just like simply represent pixels and essentially we make our hypervectors from pixel representations, it's unlikely to provide any good performance. Like even solving simple Maniz problems is not working that well. And of course, that motivates to look into what we call neural network-based representations. And this is an approach where essentially we use a neural network to form a high-dimensional to form a hypervector of an image. And largely, there are two approaches to such representation. So one is just to take some trained off-the-shelf network and just take a certain hidden layer activations of the network and treat them as if they would be our hypervectors of an image. Or another approach is just to actually design a network and train it from the scratch, trying to manipulate the objective function of this trained network in such a way that the resulting representation would be most suitable for the task at hand. And this picture provides just an overview of exactly such an approach, which was recently presented by the team from the IBM in this year, and that was published in Nature Communications. And if time allows, we'll probably have an extra slide about this approach. So I guess we can move on with this. But this representation of this slide, it sort of wraps up the part of the presentation which was related to the first part of the survey, like, get into all of the fundamentals of the area. Of course, the natural question now is like, all right, we have all these primitives. We can represent data structures, you know, scalars, images, you name it. What do we do with this? So what is applications? And this is a similar table now, which makes a qualitative assessment of the existing application domains of the area. And we at a high level, we've defined, we can talk about the 5 large areas, and we group the existing applications into like deterministic behavior, similarity estimation, classification, cognitive computing, and cognitive architectures. And here, as you can see, like according to our qualitative assessment, like the existing works with the element of the survey, they don't cover and they don't focus that much on the application areas. So it's like largely red here, and of course, yeah, it was therefore it's worth. We thought that it's worth making this effort and trying to make the classifications and identifications of all the existing applications. And we can start with the deterministic behavior. I'm not going to get into the details of any of this, any of the subdomains which we've identified here, but largely we see three types of direction when it comes to deterministic behavior. And I mean, by the way, what I mean by deterministic behavior is a situation where we would like to model maybe some exact symbolic like program, let's say execution, or some symbolic algorithm with our high dimensional vectors. And we've identified the areas such as like automata instruction and schemas, and probably also should add Turing machines. That's just an example of a simple automaton here. The second subdomain is transmission of data structures, and here two notable examples are communications and distributed orchestration, and this is an example of a recent communication scheme that used VSAs and the stream processing. And an example of this can be one of the works which was about alignment DNA sequences. That's it about in this presentation about the deterministic structures and deterministic behavior. And next we can go into similarity estimation, and that's the area where we use high-dimensional vectors as a way to represent something like some object or some data, and we use the similarity in a high-dimensional space as a proxy for the similarity between the original structures. And three subdomains which we've identified here are context hypervectors, and a nice example of it are word embeddings, the similarity estimation of biomedical signals, and also similarity estimation of images. And so I would touch on word embeddings and estimation of images in the next slides. So word embeddings, we think that there are like three influential algorithms within VSAs which are proposed in the context of word embeddings. And these are random indexing, bound encoding of aggregated language environment, usually we just call it BEAGLE, right? And also predication-based semantic indexing. And so we had a table where we specified some of the, like connected some of the references, the tasks, the data sets, a particular method which was done and the baseline. And of course, by no means this table is full in mentioning all the papers using random indexing. And also, I think as some like meta feeling when we were doing this work, I realized that looks like the activity in this direction somewhat decreased when it comes to pure machine learning, but when it comes to cognitive science, we still see a pretty high level of activity when it comes to VSA-based methods for word embeddings. But I still believe it's a pretty cool and exciting area, because it's when I was first reading these papers, I was just amazed like how much you can actually get from such a simple algorithm. This is just almost a miracle that in a single pass through your data with extremely simple operations, you can get a lot. You can get a lot from your data, and this still surprises me. But of course, a nice and an interesting question, like when it comes to the mainstream of word embeddings, is like where as these methods, how do they stand now, and what might be their potential role in the presence of what is called contextualized word embeddings, which are obtained with these large language models. And a slightly different approach to similarity estimation, but I think it's still a nice example here. Nice example in the sense that this shows how the representations of images, in the sense of neural network-based representations, how they're combined with the VSA operations, such as bounding and binding, in order to present, in order to get more compact representation of images. So it's like I feel like this is an exciting example of like taking something from existing methods and enriching these methods with compositionality, which one can get when using VSAs. And I probably wouldn't go more into the details, because I just saw that per his actually the next VSA webinar, which is going to be in about a month from now, that's going to be exactly on this topic. And I think Paris definitely knows more about this work, and I don't want to provide more spoilers about it. But it's, again, just like I was kind of impressed by this work since it combines these two aspects: data structures and compositionality of VSAs, plus sort of the flexibility of neural nets when it comes to training the encodings, essentially from VSA point of view, going from pixels to representations in high dimensional spaces. Classification next, and classification is probably right now is probably like the largest and the most expanding part of the community. And that makes sense, because there are lots of classification problems out there, but the recipe to solve these classification problems, it's relatively homogeneous. Like what we need to do, we need to take original representation, we need to come up with some way to go from this original representation into a high dimensional space, and then we need to get a classifier in order to separate the points in a high dimensional space. And also, since there was already a work last year which was providing and focusing on a review for classification, we haven't really been going into the exact details of the encodings and to the like existing approaches to tackle the part of going from raw data to hypervectors. So what we've done instead, we focused on the types of classification problems which were solved. And we've identified 3 of them. So one, and this is the largest one, is about classification based on feature vectors. Then the second one is about images or their properties, meaning like features extracted from the images, and then classification of structured data. And by far, feature vectors is the largest one. And here below on the slide, I just provide an example of a table how we were structuring our summaries of the existing works. And it was about providing a particular reference, identifying the task, and maybe this is not the best example since here task is all the same, but task can be different. Also, the data set used for this task, the basic format of hypervectors, like whether they were real valued bipolar, binary, dense binary, sparse binary, etc. Basic operations used in order to do the representations, like in order to do the transformation from raw data to hypervectors, the way how the classifier has been constructed, and baseline, whether there was a baseline, and if there was a baseline, what kind of algorithm has been used. And in such a way, we've identified a number of different subdomains within classification of feature vectors, such as classification of text, language identification, automotive data, and lots of works within the biomedical data domain, such as classification of EMG signals, EEG signals, DNA sequences, and so on. So the main idea, again, just to recapitulate, the main idea of this section was to essentially provide like a roadmap to quickly see what has been done within a particular application area of interest. And this slide wraps up the part about the application section, as we called it in the survey. And now I can see that we're getting a little bit short on time. I can probably skip a few slides here so that we have some time for discussion. But the second part is about cognitive computing and cognitive architectures. And cognitive computing is this weird term in a sense that it's a nice term in a sense that once you Google it, you can get this kind of exciting images which tell you nothing. But at the same time, there are so many definitions, and many people have different opinions on what is cognitive computing. So in our case, what we were referring to when talking about cognitive computing in the context of VSAs was talking about holistic transformations, analogical reasoning, cognitive modeling, and also computer vision and scene analysis. When it comes to cognitive architectures, I don't have any further slides on cognitive architectures, but we've identified several approaches on where VSAs were used as a representation framework for cognitive architectures. And probably the most well-known approach is Chris Eliasmith's spawn architecture. But then we also found a connection to the LIDA model, to HTM, also to associative projective neural networks, and we've including modeling of memories as a part of cognitive architectures. Even so, some of the works on memories, they can be seen as just standalone works, which sometimes are connected to cognitive modeling in the sense that models are being compared to the results in human subjects. But we still feel that memories are essential components of cognitive architectures. So it's probably a valid way to consider model memories under the umbrella of cognitive architectures. And so when it comes to holistic transformations, there are several primitives which and all of them they have been proposed a while ago, and probably the simplest one is this transformation of data records, and here I have one table, and that's from Pentis paper from 1997. And that is essentially the ideas described in that paper. I think they've led eventually to very famous example. I'm pretty sure all of you have heard of it, and probably some of you were actually, you know, dragged into the area by this example, which is like, what is the dollar of Mexico, right? That's one approach to holistic transformations, and the other one is about systematic transformations, and there we saw three patterns. So the first one was like manually constructed systematic transformations, and this is just like, you don't have to focus on this. This is just like from Tony Plate's paper, also from year 1997, I believe. And then Pentive demonstrated learning from examples where we don't actually do manual construction, but we have like, we define the basic structure of the, like how the transformation is connected, and then just we accumulate the transformation vectors over several examples. And that in that paper, which was probably year 2000, there was this example, like if X is a mother of Y, then X is a parent of Y, and it was shown that we can learn this association from examples. And the third one is optimization-based transformation, and this is a work by Jenny Newman, where she was using gradient descent methods to learn transformation vectors when given certain data sets, given training data sets, which were used by the gradient descent to find transformation vector. And like my personal feeling is that like these exciting works, and there were a few follow-ups, like maybe about 10 years ago or so, but I haven't seen recently any works in this particular direction. And so I think this is an exciting stuff. It's pretty similar with analogical reasoning. So we have a series of works by Tony Plate, where he was modeling this simple analogical episodes of different types of similarity, representing them using HRR framework, and then measuring the dot product between the representations, and based on the dot product, distinguishing different types of similarities, as kind of highlighted in this table. And so I feel that this is pretty exciting direction for work, but probably the most recent paper in this direction we've identified was maybe 2012 or so. But I feel like there are still lots of things to be explored here, but it's also nice to keep in mind that quite a few works have been done in this direction. When it comes to cognitive modeling, we've identified several directions, such as just like using VSAs as a component of cognitive models. Then also a particular direction with several works is modeling of human working memories with hypervectors. And also another direction is solving some cognitive tasks, like making models for solving cognitive tasks. And Raven progressive matrices, they have generated quite a few works. Also, there were attempts to do the Tower of Hanoi task. And there are also some works by crystallothmic groups to do some general purpose, like rule-based following, and some works on logical based inference. And this slide wraps up the part about cognitive modeling, and ideally I would like to go into the discussion, and only the aspect of the discussion which makes a connection between VSS and neural networks. But since it's already 1 p.m., I feel like I better to stop here so that we have some time maybe to discuss some of the things which I've already said. What do you think, Evgeny?
Yeah, thank you very much, Denis. I think you're right. So we are, now it's 1 hour since we have our webinar. So let's have a discussion. So I hope we will get some feedback from the audience. So please unmute yourself and speak up.
Jump to this slide.
So let me see. Anybody? It's either too late for some of the people in the audience or too early for the other part of the audience. And for the for California people, it's probably time to lunch. Time for lunch,
yeah.
right?
Yeah, maybe I can say maybe the last thing. If there, I mean, I was kind of, yeah, it was, you know, it's hard to have a question probably since I was to a large extent maybe talking about the things which are well known in the area. But so what I just wanted to mention also is that, like, if this autumn we had an effort in giving a course on HD computing, and the recordings of the lectures, they are available either on the HD computing website, and here's a print screen from that page, and it also links to the course web page at the Redwood Center website. And so I just wanted to mention it in the context that many of the topics on which I briefly touched today, there are recordings of the lectures which provide, you know, a much deeper dive into different aspects of the area. And so if you feel that there is any interest in going into like, you know, getting an overview of some of the areas, I think that might be a nice place to start.
There is a question in the chat, Denis, from Nathan. I'm curious of your thoughts on the memory augmented neural nets in Nature from earlier this year.
Yeah, so I think yeah. So my thoughts on the memory augmented neural networks. Yeah, I think it's first of all, I like the idea that you can add that you can modify your cost function in order to include some of the constraints which would force the network to sort of train to learn better hypervectors, in the sense that, you know, instances or hypervectors for images which belong to different classes should be nearly orthogonal to each other. I think that was a pretty cool idea. And in general, I think it was nice to make this connection to sort of bring the ideas from HD computing to memory augmented neural networks. Even so, also I should mention that some of these ideas were brought earlier, maybe like 5 years ago, so by the group at DeepMind. And like in their neural Turing machine work and the work where they add FHRR vectors to LSTM. I think we briefly discussed this work in the survey too, and of course, yeah, it's also of course exciting to see how this is being mapped to the PCM devices, how this is being mapped to hardware. I think that generates lots of excitement. The intersection of the three, how you can use primitives from HD computing, combine them with neural networks, and also include an element of hardware implementation, unconventional hardware in particular.
So Nathan sends thanks to you for the answer. Well, let's see. Let's count to 5 and see if there are any volunteers to ask or to contribute to the discussion. Well, if not, I personally think that there is a great value in such a presentation. I mean, we all working with this with the VSA and HD computing, well, tend to focus on particular problems. And sometimes we lack this kind of broad view, so which is, I think there's a great value in this presentation by giving this broader view. So I want to remind you that we have our mailing list. So in the case of questions, so please submit your questions to the mailing list or write to Denis directly. As for me, so I just want to say that, well, today in Sweden, we celebrate one of Christmas holidays, which is called Saint Lucia Day. And we light the candles, so to welcome the lights in this darkest time of the year. So, and I want to send some of our lights to all of you, and hope for better times, so lighter times in many respects. So we will resume our regular webinars after Christmas and New Year in January. So stay tuned. And yes, and now I even spotted one question. So, but I will finish my greetings to you. So I wish you Merry Christmas and a Happy New Year. But now I want to get back to the question in the chat. Any ideas on contributions to self-organized criticality? Denis.
Yeah, I must admit that I've no good conceptualization of what is self-organized criticality. So I guess, yeah, I cannot answer to this question, unfortunately.
But maybe, Jill, so this might be a good topic for the one of the upcoming webinars next term. So please drop me a line. So I will be happy to include it in our schedule.
Yes, maybe I'll know something by then.
All right. Okay, that was a tricky question. Yes, I see. Okay, but all right, everybody. Thank you very much for attending, for staying with us, and stay tuned to our spring session.
Can I just add that?
Sure.
Thank you, Denis, for the great talk. I just wanted to mention that during this Christmas time, you can work on your submission for the IGCNN 2022 special session, which will be on hyperdimensional computing and vector symbolic architectures. And I will be one of the hosts, and so I will be glad if you could submit some of, as Denis said, there are many applications and the scope is so large that we need more advances in every area. So we are welcome to host you in Italy, and I hope to see you all together there.
Sure, that's a great announcement. Thank you, Antonello. So yes, please send the contributions to the special session. All right, thank you very much, all. So we end the summer session 2021. So Merry Christmas and a Happy New Year to you all. Bye.
Bye-bye.
Buon Natale.
Good Christmas.
Merry Christmas. Bye-bye.